Imagine a world that's totally isolated, completely self-sustaining, and just suspended deep in the freezing, crushing abyss of the ocean. No sunlight, no fresh air from the outside. Just a sealed metal tube completely surrounded by millions of tons of hostile water. Welcome to today's Explainer. We're jumping right into the awe-inspiring engineering and hidden physics of nuclear submarines. We're going to look at how these vessels basically act as miniature, lonely planets, severing absolutely all ties to the surface world so they can operate independently in literally one of the most extreme environments on Earth.
Okay, let's dive into this. The central mystery we're unpacking today is all about ultimate survival. Seriously, how exactly do you keep over 100 human beings alive, comfortable, and combat-ready in a sunless, crushing void for up to 120 days at a time, without ever surfacing, without taking a single breath of outside air? Well, to understand this, we've got to look past the weapons and the sonar and look directly at the incredibly complex life support and power generation systems that make this seemingly impossible feat a reality. You know, you can really think of the modern nuclear submarine as a kind of ghost ship. Once it slips beneath the waves, it transforms into this self-sustaining leviathan. In the past, older diesel submarines were essentially just surface ships that could hold their breath for a little while, right? They eventually had to come up or at least stick a snorkel out of the water to run their engines and recharge their batteries. But a modern nuclear submarine, it is entirely severed from the surface. It's a completely closed system that has to provide absolutely everything its crew needs from within. And the stakes for maintaining that closed system are unbelievably high. Just inches beyond the hull of the ship, the temperature of the deep ocean is typically a freezing 39 degrees Fahrenheit. That's about 4 degrees Celsius. Basically, picture the temperature inside your kitchen refrigerator. The thick, high-yield steel hull conducts internal heat right out into that freezing water. So without the ship's massive internal environmental controls and electrical heaters actively holding that freezing void at bay, the crew would quickly perish from the cold, way before the immense pressure of the ocean ever became an issue.
Which brings us to Section 1, Heart of the Leviathan, the pressurized water reactor.
To fight off that intense cold, power the entire ship, and actually keep the crew alive, you need a truly unbelievable amount of energy. U.S. nuclear-powered warships use what's called a pressurized water reactor, or PWR. This is a super-compact, incredibly energy-dense nuclear reactor, because, as you can imagine, space is the absolute most valuable commodity on a submarine. You can't exactly have sprawling power plants in there. The PWR is perfectly suited for these tight confines because it concentrates massive power generation into an incredibly small footprint. It does this by using water kept under immense pressure, which allows it to absorb staggering amounts of heat without ever boiling into steam. Now, what's really interesting about this is the physics behind it. It's an incredibly elegant, closed-loop, four-step dance. First, the primary loop circulates water right through the reactor core, superheating it. Second, the superheated, pressurized water passes through a steam generator, transferring its heat to a completely separate secondary loop of water. And because these two loops never mix, the radioactive elements stay completely trapped in that primary loop. Third, the secondary water boils into steam. And fourth, that clean steam drives the massive turbines that turn the ship's propeller and generate literally all of its electricity. This brilliant design gives the submarine almost god-like advantages over its diesel ancestors. Most critically, this entire process requires absolutely zero oxygen to generate power. Think about that. Zero. There's no combustion. And because nothing is burning, there's no exhaust vent out of the ship. And you don't need to waste any precious interior space storing massive tanks of liquid fuel or intake air. The ship can just stay deep underwater, completely invisible, running at top speed without ever needing to breathe the atmosphere. And when we say endurance, we literally mean decades. A modern submarine's reactor core is designed to last greater than 20 years. In fact, in newer classes like the Virginia class, the core is actually designed to last the entire 33-year lifespan of the ship without ever needing to be refueled. Just think about that for a second. Over 1 million miles of boundless energy for propulsion, heat, and life support, all originating from a single fueling. It's mind-blowing. Moving on to Section 2, Breathing the Ocean, Creating an Artificial Sky. Because as amazing as it is, limitless electricity doesn't keep a human crew alive on its own. We need air, and we need water. Inside the sub, a highly advanced system called CAMS, that's the Central Atmospheric Monitoring System, acts as an automated artificial sky. And this brilliantly illustrates how the sub sustains life. It uses mass spectrometry, which literally bombards gas molecules with electrons to identify them, constantly sampling the air throughout the ship. It meticulously monitors oxygen, carbon dioxide, carbon monoxide, and even trace gases like freon and hydrogen. It does all this to ensure the atmosphere inside mimics the absolute cleanest surface air possible. But here's the catch. They can't bring enough oxygen with them for a months-long deployment. So the submarine has to literally breathe the ocean. Using all that immense electrical power from the nuclear reactor, the ship pulls in the freezing, crushing seawater from the abyss outside and chemically transforms it into the essential elements of life. The sub pulls this off in two pretty miraculous ways. First up is the electrochemical oxygen generator, or EOG. This beast passes a massive, direct electrical current, we're talking about 1,000 amps, straight through purified water to split the molecules apart. The hydrogen gets pumped overboard, and the pure, breathable oxygen goes straight to the crew. Second, for drinking water and equipment cooling, the ship's distillation plant boils seawater into vapor, leaving all the salt behind, and then condenses it. To put that into perspective, this system alone creates a staggering 10,000 to 40,000 gallons of fresh water every single day. Which takes us to Section 3, exhaling into the void, erasing the human footprint. You see, creating oxygen is really only half the battle, because when you're trapped in a sealed capsule, a buildup of human exhalation is deadly. You absolutely have to scrub the air clean of CO2. Submarines use a chemical called monoethyleneamine, or MEA. This is a liquid solution that acts as a regenerative scrubber. So the crucial point here is that through a process called a Lewis acid-base reaction, the MEA chemically binds to the carbon dioxide molecules suspended in the air. It literally pulls the toxic gas right out of the atmosphere so the crew doesn't, well, suffocate on their own breath. And this all happens in a continuous regenerative cycle. First, the stale submarine air is blown over woven stainless steel screens that are completely coated with flowing MEA. In just one single pass, it strips out 70 to 90% of the CO2. Then comes the genius part. They take that CO2-loaded MEA, pass it into a separate column, and heat it up. That heat forces the MEA to release the CO2, completely regenerating the chemicals so it can be used all over again. Finally, the ship takes that pure carbon dioxide gas, compresses it, and forcefully exhales it overboard, safely dissolving it into the dark ocean outside. Let's move to Section 4 and see how this builds to our conclusion, the final biological limit, the machine versus the human. So, we've got this incredible machine that can generate power for decades, make endless water, and chemically synthesize its own perfect sky. But the ship doesn't operate itself, right? And that creates the paradox of submarine endurance. On the engineering side, the submarine's capabilities are almost godlike. Endless electricity, infinite oxygen pulled right from the water, tens of thousands of gallons of fresh water. But on the biological side? Well, the crew requires calories. And while a submarine can magically make air and water from the ocean, it definitely cannot make food. A modern nuclear submarine is ultimately bound by a rigidly finite pantry. Despite all the multi-billion-dollar technology on board, the mission hard stops when the food runs out. And for a hungry crew of 110 to 140 sailors, no matter how creatively you pack the ship, that absolute biological limit is roughly 120 days. Former U.S. Navy submariner Jeffrey Knight put this biological reality into perspective perfectly. He noted that at the beginning of a patrol, food is stowed absolutely everywhere. It's totally normal for sailors to physically walk on layers of food cans in the berthing areas until they eat enough to finally take the floor level down to normal. After about 110 days, they are basically surviving on dehydrated fruits, cake mix, and maybe a single canned ham. As he joked, the absolute max limit is 120 days. Or exactly 5 days after the coffee runs out, whichever comes first. It really is a fascinating juxtaposition, isn't it? This effectively infinite machine bound by a finite pantry. Because U.S. naval reactors require human monitoring and maintenance. If the crew were to ever run out of food and perish, the reactor wouldn't just melt down. Instead, the highly automated safety systems would detect the lack of proper maintenance and safely shut the reactor down. The ghost ship would lose its forward propulsion, and depending on its buoyancy at the time, it would just slowly drift up to the surface or fall silently to the crushing depths below. The physics of submarine endurance is an absolute triumph of engineering, turning the most hostile environment on Earth into a completely survivable habitat. But it leaves us with a pretty profound realization. We have already built machines capable of near immortality, but we are still tying them to the fragile, calorie-dependent constraints of human biology.
So as we look forward to exploring deeper oceans and eventually even deeper space, you have to wonder, how will we eventually overcome the fragile constraints of human biology? Thanks so much